Okay. Hello, everybody. My name is Ben Campbell, and today I'm going to be going through all of the electrical systems that are on board the ADRASTEA spacecraft. Now, see this hunk of junk right here. I'm sure it looks like a complete nightmare of wires. It looks like a mess right now, but I promise that's on purpose. The reason why is when everything is all exposed like this, I can give you a grand tour of all of the things that are going on here. I can explain each and every wire, um, where they're connected, how they route through, what they're used for, how they interact with different software operations, all of those different things. So I'm specifically recording this right now. Um, Today is currently May 29th. We're just a few days away from having this thing basically integrated all together for the final time, where like all of these wires all on the outside here are they're all gonna get shielded, staked down. All of these enclosures right here for electronics, they're going to be sealed up for the last time. Um, all of these things are going to be all tight packed and ready to go to space. And so um, right before that happens, I'm able to give you a grand tour of everything, and hopefully you can learn a thing or two. It is a bit much, so like there are literally hundreds of wires on this thing, and I'm going to do my best to explain what each and every single one does, and then so I'll be explaining all of the wires, all routing throughout this thing, and then I'll also be able to walk through how some of the PCBs are designed, um, how they operate and are used, and I'll be going through some schematics and PCB design stuff in Altium. So I'll kind of swap between like the camera here and another monitor I've got set up for looking at Altium schematics and everything. So um, all of the stuff on the table right here, and then I've got some other stuff back here that I'll go over a little bit later. Um, all of this stuff is in kind of a delicate position right now. So the way that I'm handling this, I've got gloves, I've got an ESD bracelet, I've got an ESD jacket. All of this is plugged into an ESD mat, which is then connected to the ground outlet on, or to the ground pin on an outlet in the wall right now. So um, if you're ever dealing with spaceflight electronics, you should only ever be interacting with them when you have proper ESD protection on. Otherwise, you risk even just the slightest little bit of static from like your clothes rubbing together and then you touch something. Um, that spark might not seem like much, but really that is thousands and thousands of volts just jumping across a little component from your finger, and that can completely fry electronics. We've had several things get fried in the past. I've seen it happen. It's a bad time. So make sure you have proper protection on whenever you're dealing with any of this stuff. So um, got that. So I'll give you kind of the rough summary of all of these different systems, what they're doing. So this, if you see this kind of aluminum enclosure right here, kind of where my hands are, in this hunk of junk right here, and I'll actually move this camera really quick. So kind of that to kind of center it a little bit. Let's see, focus. Yeah. All right. So this aluminum enclosure right here, with these like white, blue, yellow, and green wires all kind of going through it. So these are the electronics for a system we have called Jupiter. And I'll actually let me make this a bit. Let me zoom this in a bit so you can see a little bit better. Okay, there we go. Something like that. Okay. So this whole aluminum enclosure right here, that is, this is Jupiter. All of these, this little chunk of stuff, this is all Jupiter. So this is basically what our payload interacts with the rocket through. This system is responsible for command and data handling, power management, communications, all of that stuff, all of the core functions of the spacecraft. And so it's got a handful of boards on here. It's got one board on the bottom. This is our power board, or basically an EPS. or electrical power system. So it's on the back right here, and I'll angle stuff around a bit. And you can kind of see this other board kind of stacked on top of it. This is our avionics board mounted on that. And actually, let me rotate this around really quick so you can kind of see. So we have this bottom board is basically our EPS board. This second board right here is the avionics board. So this has a handful of sensors and logic systems that these two boards right here mount to. So this right here, this is an ATmega 2560. So this is basically, this is an auxiliary system that basically it's a microcontroller with loads of GPIO and analog inputs. So we can use this for some data recording and transmission stuff, kind of as a slave system to this, the flight control unit. So this is basically a Raspberry Pi 3B Plus. You can kind of see it on here. It's on top of this stack. And so the FCU, or the flight control unit, this is the main brains of the operation. This is where all of the core logic is held. This is where all the main flight operations are controlled. So this is the main brains. The Mega is basically like the arms, or kind of like Igor, like pulling a bunch of levers and stuff in a lab. Avionics is basically the lab where that takes place, and then power board is power for everything. So the way that we have all of that set up, all of these wires, so these interact with both the launch vehicle and the rest of the experiment hardware here. We've designed this to be very modular in nature, so that different functionalities can be done across different missions, because our main intent with this system is to actually have it be reused on future space flights. This is going to be the first flight of this stack of boards, and ideally we'll be able to get it back after the flight and refly it on a future mission in 2025. So there's a bunch of different functions all on here. So you can see these two kind of metal cylindrical things right here. So those are some high vacuum connectors. Those are 23 pins each. Right now we have them assigned to where, so this bottom one right here, this actually goes out to some wires, to some connectors right here. So these two D-sub connectors right here, these are where we actually plug into the launch vehicle itself and connect to the rocket's power system, the onboard computer, the telemetry system, all of that stuff. So this connector right here, this is basically where we get power from. So the rocket sends power in through these, and then those come in here. They do stuff. All of these boards then control and operate this equipment up here, get data from it, process it and save it locally on here, but then also transmit a lot of that data out through this connector, which then is picked up by the rocket. The rocket can then interpret a bunch of those signals and then beam them down to the ground. So we have a live telemetry link with this while it's in space. So this connector right here, so the power that we get in from the launch vehicle is 28 volts. We can get up to 4 amps at any given instance. So we have several lines that are activated at different times. During the year before the launch, we're actively going through review cycles with NASA personnel, and we're talking with them and figuring out, all right, when do we want certain key events to happen during the mission? And we work with them to collaborate on when certain lines get activated at certain times. So there's two main types of lines that can be activated. You have GSE lines, or ground support equipment, or ground support events. Those are basically some 28 volt signals that can be activated anytime between T-minus 10 minutes from launch and T-minus 3 minutes from launch. Those, you can basically have them activate and turn certain things on before your flight. So you can have stuff on here, start prepping data files, start booting up certain systems, all of that kind of stuff. So you can have 2 GSE lines, and then there are a handful of TE lines, or timed events. So TE lines, you have TE 1, 2, and 3, which you can activate at different times. Those are like, for example, you can have one activate at around like T minus 70 to 80 seconds or so around when skirt separation occurs. That's when you can, start ejecting things out, start deploying things, start trying to have a camera target on something in space now that there's, you don't have a wall in the way, or different things like that. You can have stuff like a pseudo apogee indicator, or like a shutdown warning, like before power to the payload section of the rocket starts getting shut down. So then you can have ample warning to switch to like internal power, something like that. So you can schedule them depending on however you want your experiment to operate and what's available with NASA personnel. There's also similarly two TE redundant lines. They're called TERA and TERB. So those basically operate as kind of redundant lines on separate power systems, so that, like, even if other parts of the rocket aren't working, at least these redundant lines should activate and be fine. So those can be helpful with, really like critical events, where if nothing else works, at least have those and have the thing work. And so each of those lines are 28 volts. Sometimes they can surge up to around 34 volts during, when you're on the pad and you're in the middle of transitioning between power systems from the ground support equipment or the launch vehicle, different stuff like that. But, they're pretty high voltage systems. And so we take those, that power comes in through this connector, comes into here, goes through some wires, and then goes to basically this corner of the power board. If I go and actually flip this around, you can actually see some of the circuit stuff right here. So on the other side of this board, there's a handful of headers that are sticking up here that a bunch of these wires go and plug into and then are locked down into. So you can kind of see on here, there's a handful of pins assigned like GSE1, GSE2, some ground pins, TERA, TERB, some ground pins, TE1, TE2, TE3, ground, and then also some battery leads that I'll talk about in a little bit. So basically all of those things, actually I will, let's see. Let me pull up Altium really quick. So I've got some of the schematics right here. So I've got the schematic right here, and there's other things on the page. And then I also have the actual production file, the actual 3D model and like layout of all of the traces and everything on here. So if I flip this around really quick, let's see, there we go. So power comes in over here at the top of the board, comes down, and then the power gets split into, so we've got these diodes right here. These basically all then funnel to a general 28 volt plane. And then we also have them branch into, we've got some little voltage dividers here, which we can use for basically detecting logic level voltages of when each of these lines activate. So we get certain stuff powered on, but then we can use them for timing, where it's like, all right, we get a reduced voltage signal that we can pick up on, like an Arduino or Raspberry Pi type device, some sort of logic controller, pick it up at a lower voltage here and get picked up. So then we can, schedule certain events to happen. And so these diodes basically help prevent the signals from interfering with each other before hitting that 28 volt plane and hitting these voltage dividers. The schematic kind of shows, so they all go through here. So GSE1 through TE3, they all go through these diodes into a 28 volt plane here. And then also they go through some voltage dividers right here. So this is what those look like. This brings the voltage from something ranging between 28 to 34 volts down to something that's capped out at around 5 volts. So you can pick them up pretty easily. So those are identified by the ATmega 2560 on here. And then each of the voltage levels that we operate on for everything else. So we have 12 volt, 5 volt, and 3.3 volt systems, or like power lines that we can operate the rest of the equipment with on this payload. And so the big 28 volt plane that is that all of these diodes dump to is it's so that 28 volt plane. There's 3 DC to DC converters on here, which help bring that voltage level down to something a little bit more manageable for certain systems. If we want certain stuff to be high voltage still, that routes out to some other experiment systems, say we have some really beefy motor or something that we want to run, we can have 28 volts output directly to whatever, but 3.3 volts and 5 volts are common voltage levels used by a lot of logic controllers. And then we also have 12 volts for, if you want kind of some intermediate level like motor, you can do that. And so power comes in up here, goes through these diodes and these voltage dividers. And then the 28 volt output that comes out of these diodes goes to a big plane that's then tapped off of by these 3 converters. And then the power from here then goes up to this output right here. So this set of outputs right here is raw power outputs from the DC-DC converters. So we've got some ground lines, which is, you never have too much ground. We've got 3.3 volts, 5 volts, 12 volts, and then 28 volts. So that then goes to the avionics board, which I'll talk about in a little bit. We also have, so this section right here, this is the outputs of just the logic level voltage signals from each of these lines. So you've got GSE1, 5 volt, GSE2, 5 volt, all the way through. Then you've got this battery level and battery trigger stuff right here. And I'll explain that in just a sec. So both of these sets of pins go through some right angle header connectors, which then plug into a mating set of connectors that are on the avionics board. So then it goes and starts powering things through that board. So now, so we have the main power from the rocket. Now that is active from, power is available from the rocket from T-minus 10 minutes until around, T-minus 10 minutes until around T plus 5.5 minutes in, or around, so formally it's T-minus 600 seconds, and then up to T plus 335 seconds. So that is the maximum amount of time that we can be receiving power from the rocket and actively doing things. Anything outside of that time, so like if we want to have things operating during re-entry or splashdown when things come back down, we can rely on some internal battery systems to do that. And so what we have here is we have, it's not shown on this board, but we have some batteries. I actually have some of them exposed right here. So some of these right here. So we basically have a nominal 7.4 volt battery source that we can store inside Jupiter. And what we can do is basically trigger that system to activate just a little bit before power from the rocket starts to shut down. And the way that we do that is we have this little battery latch circuit, which I will pull up over here. So basically what we have is, so we have a solid state relay in the middle that we have this battery latch trigger. This is basically just a GPIO signal output from the avionics board. And what that does, it goes through a current limiting resistor, goes through and basically trips this relay and allows battery voltage to start flowing through into that 28 volt plane. So there is a blocking diode that keeps that 28 volt power from reversing through. But what it does is that basically it's setting up voltage right here. It's allowing the battery to start pumping power into here so that as soon as that 28 volt line deactivates, then there is battery voltage that's immediately ready to dump into that plane and keep things turned on. So we have that, and then we also have this little voltage divider right here, which basically what that allows for is this nominal 7.4 volt signal that goes through here. We can basically tap it off right here, or tap a little bit off right here to then allow a voltage to be brought into one of the analog lines on the Atmega to then basically be used as a battery voltage indicator, so we can see how full the battery really is. And so we can have that, and then as soon as we want to turn things off, we just turn this battery latch trigger GPIO output to be a low or off. That deactivates this, which then stops power going through here, turns off all of the power to the whole to the rest of the spacecraft and everything. So those two pins right here, so this this bat trig right here, that's GPIO being received from the avionics board, goes through here and does things. And then the battery level is an output from this power board that goes into the avionics board and is an analog voltage to be used for battery measurement. And then this other thing that we have that is down here. So one thing we thought of that, a few months ago when we were working on some of this, we actually had some problems with basically trying to get some smooth signals or smooth voltage levels coming out of the DC-DC converters. They work, they get to a good voltage, but they're a little noisy. They got some fluctuations on there that we didn't really like. And so before that we had thought of putting basically a little like proto board type area in some of the free space that's on the board, so that if we need to make any modifications, we can add some through hole components and make that happen. And that turned out to be a really good idea. And so we actually ended up using it to mount, you can kind of see there's some capacitors on here. So we have some 100 microfarad capacitors on here, and each of those are tied to the outputs of each of these three converters right here. That helps kind of really smooth the signal down, or like smooth it up, and get much better voltage levels coming out of here that are a lot more stable. It also helps kind of reduce the impact of certain transient behaviors, which, like when switching to the battery power rather than the rocket sourced power, this helps kind of smooth that transition out, so we don't have to worry about instantaneous like brownouts, or where things just get underpowered and quickly turn off for a split second and turn back on. So that helps smooth that out, and so that's really good. So that's most of the power board circuitry right there. Next, we've got the avionics board, which is really kind of buried in here. So you can kind of see a little bit in there. You can kind of see on the top there's a handful of connectors, but it'll be easier to see in Altium really quick. So what this looks like, let me pull this up. So you have this version. So basically we have the Pi and the Mega stacked on top of it, and then over here, so we've got these connectors right here. And if I actually go to the back side, so we have power in coming from the power board just underneath it. So we've got a set of right angle headers, and this little some of the silk screen right here. This is just kind of showing where those pins are oriented. And on the power board, there's some as well, but just in the opposite direction. So if I flip this around, you can kind of see them there. So they're right there. We've got pins on this side here, right angles on here and here, which then go to the avionics board right on top. So avionics board, so we've got those right there. And so those traces then go mostly, so like the power gets redistributed up here, so that then we can branch things out into more pins if we want, and go out to more devices, whatnot. And so we've got ground, 3.3, 5, 12, and 28 volts right here. And then you see a whole handful of other things all here. So these are all different possible data outputs or inputs that are connected to the periphery electronics that go out through this other high vac connector that goes out to experiment systems, or goes to the high vac connector to the rocket to then go to this telemetry and data connector right here. So power is up here. This right here, so this I2C, RX, SPI, and GPIO section right here, this is a lot of your basic like sensor and general like logic device communication protocol stuff right here. So we've got some pins where basically on the Raspberry Pi or the flight control unit, we have broken out I2C lines right here. We have some grounds right here. We have this RX right here, which I'll talk about in a little bit. That's part of a serial connection. We have this, so we have SCK, CS0, CS1, MISO, and MOSI. Those are some SPI specific lines. So you've got your clock line, you've got your master in, slave out, or master out, slave in. Then you've got your chip selects right here, which help you select between some different devices. Then we've got G1 through G10. Those are just general GPIO 1 through 10 on the Raspberry Pi. Those are just use them for whatever you want. If you want to do PWM, if you want to do just basic up, down logic signals, or high or low, whatever, you can do that with those. And I won't forget about that RX thing. I'll talk about that in just a sec. Up here, we have some analog lines right here. So basically what this is set up as is that we can have lines come in from the other experiment hardware and plug into here, and it can be detected and saved by the Mega that's underneath this through some analog lines. But you can see that they're kind of doubled up. They're all connected to each other. So that's set up so that you can have experiment analog data coming in through one set of connectors, and then the other set, you can have it branch out straight to the launch vehicle if you want. So the launch vehicle can take in up to 10 different analog signals on different independent lines. So that's what this is right here. And then this section right here, so this D1 through D16. So this is, there's a digital interface where basically you can send basically 16 individual bits of data, basically by literally just driving GPIO signals high or low to act as the individual bits, like zeros and ones in some signal. So you can set a whole set of these to be whatever you want, ones and zeros in positions 1 through 16. And those then also operate in parallel with, so this DS right here. So this is a digital strobe line. Basically, with each pulse of that is when you update the values on each of these D1 through D16 pins right here. So you can then send a bunch of individual bits and everything all through here. This is something that the launch vehicle can interface with, and so we have that capability on these boards, although we aren't using that functionality on this specific flight. And then this RSG and RSD pin. So these are connected with this RX pin right here. So the RSG and RSD, those are just short on this board for RS-232 data and ground. So the rocket can take in a RS-232 serial input, which is basically, think of it like a serial or UART. Mine is just sending raw text over a set of wires, but instead of so UART, you're using kind of lower voltage logic levels. With RS-232, you've got like higher voltage and also like positive and negative voltage and stuff. And so how we have this set up is this RX line. If we have anything on the experiment that is outputting some sort of serial data that we want to have recorded, we can have it get picked up right here as the RX. So this is where the Pi is receiving. This is the RX right here. So the UART pair or the UART port on the Pi can pick up RX right here at 3.3 volt logic, takes it in, and then the TX line on the Pi actually then goes to I can go here. So the TX line on the Pi actually goes to a little RS-232 conversion chip, which is right here. So that conversion chip then basically takes that signal, changes the voltage levels that come out of it, and then that goes to this RSD value here. So this is basically the TX of that Raspberry Pi UART port, but at voltage levels that the rocket will be able to actually understand. And then this RSG is just another ground line that is tied to that RS-232 connection right there. So that's kind of what that is right there. And then over here, we have a handful of sensors right here. So the models, they aren't all showing up right now, but the footprints are all there. So we've got basically a suite of sensors right here for basically anything that you could anticipate wanting on a suborbital flight. So we have a magnetometer, we have a pressure and temperature sensor, we've got an IMU right here, or inertial measurement unit, which basically is on this case or on this system, this IMU is an accelerometer and gyroscope. We have a high G accelerometer right here, which helps us detect acceleration spikes at higher levels, like what would be experienced during the launch. Where you're going beyond the limits of this IMU right here, which you can get really good precision data, but your acceleration threshold can only go so high. The high G accelerometer on here can take upwards of 100 Gs, and so that'll be there. Then we have this temperature and humidity sensor right here. We have that. And then the schematics for this stuff, let me swap over really quick. So we have these right here. So these are the launch vehicle and experiment connectors headers. So these are those four big bundles of connectors in the top right of the board I showed just a bit ago. And then we've got these Jupiter power board headers right here. Those are those right angle connectors that go on the underside of the board. And then we've got over here, we've got all of the different sensor schematics for each little one. So they've got, you've got your power lines, you've got your I2C, SCL, and SDA lines that are talking on here. You've got your pull-up resistors, all of that stuff. So we've got that over there. We also have an I2C level shifter. So this allows us to basically set up the Mega on here as a slave I2C device to the Pi. And since the Mega operates at 5 volt logic and then the Pi works at 3.3 volt logic, we use this level shifter right here to allow them to interact with each other without having to worry about like improper voltage matching stuff. So we've got that. We've got the Pi right here. It's got its pinouts right here, nothing too crazy. And then we've got the Mega right here. We've got our digital, analog, and we also have our launch vehicle signal detection stuff right here, along with our battery trigger and monitoring. Then we've got this UART to RS-232 chip converter or converter chip. So this basically takes in UART TX from the Raspberry Pi, goes through this chip, and then outputs RS-232 data, which then goes and gets picked up at one of these connectors right here. So yeah, this RS-232 data line right there. So that is the avionics board. So then let me swap back over here really quick. So that is the power board, the avionics board taken care of. And then we've got NAT Mega 2560 under here, which is basically an Arduino Mega, but in a more condensed form factor. That's all it is. And then a Raspberry Pi 3B Plus. So those are both stacked on some headers on top of it, which you can kind of see You can kind of see some of there. And I have a second set of headers to bring this Pi up a little bit specifically so I can access some of the USB ports for some debugging stuff that we're doing right now. But so we've got that, and I can go and kind of see, you can kind of see the megas underneath there. Let's see, yeah, so right there, it's on some headers as well. So we've got that. And then the way that these are all connected, so we've got a handful of these wires, which these, we just got those simple like DuPont like header connectors right here. So this is a female. So we have a handful of those all on these high back connectors right here. So you've got a handful of female connectors on here, and then we've got male pins on the actual boards that they plug into. If I rotate this around, you'll be able to kind of see a little bit more what I'm talking about. So you can kind of see right here, all kind of in here. So normally, if you would just take those kind of wires and plug them in, so like for example, I've got some right here. Let me grab them. So if I were to just take, one of these and then plug it in, like, yeah, you have an electrical connection, but then as soon as like intense vibrations start to occur, that can just rattle the thing apart and make a disconnect. We don't want that to happen. And so what we actually came up with a while back was this thing that we call cable combs. So cable combs basically are a set of little flexible 3D printed comb-like structures that we actually have kind of interlace on top of each other to basically hold the connectors down to keep them from popping up. So you can kind of see these little white things right here. They basically work where there are these little combs that, if I orient my fingers right, so one comes in one way, one comes the other way, and you basically have them overlap on top of each other and get screwed down, and then the holes between them are just big enough for the wire to go through, but not the connector. So you can kind of see right here, and I can try to lift this up a little bit maybe. Actually, I'll just move the camera. That'll actually be easier. So, so you can kind of see, there you go. So you can kind of see it right there. So, so two sets that are kind of on top of each other. Let me move this camera around a little bit better. So you can see them, focus. Yeah, so you can see them. They're just stacked on top. They hold the connectors in right there, and then they get screwed in on the sides with some little standoffs. And so those hold that together, and that will that'll hold everything together. And so I'll put this camera back. So okay, all right. So that's how that all gets held together. Those go through the high back connectors, and then things start going out to everything else on the outside. So let me check this. All right, so got that. So the wires go through, and then you'll see there's this kind of like red goop that we have here. So this is some RTV. This is let me actually check really quick which kind it is. So we've got two tubes of this stuff. We have one set for internal potting and then one set for external potting. So these are actually recommended by NASA. So this is what we use. So we have some of this. This is some clear RTV sealant that we basically put on. So we put on some of the inside. Let's see. So if you can kind of tell, there's a little bit of like a clear epoxy stuff kind of put around these wires up in here. And then we have this red stuff on the outside, which is some of this stuff. So this is another set of RTV. This is a little bit better for thermal properties. So since this is actually going to get exposed to atmospheric reentry, that's what's going to be there. So those will both help keep things sealed and keep things from getting too burnt up or anything during reentry. And then when things splash back down in the ocean in the end, there's that. So we have some of that there to help seal things, and we've got wires come through. So all of these wires. So these black and red wires on this power line, you can probably guess pretty easily. Those are power and ground. And then this blue line right here, this is specifically a branch off of one of the power lines to a remove before flight switch that we have right here. I'll explain some of those in a sec. And then this black and white set of wires right here. So this is actually the RS-232 serial line right here and the ground line basically wrapped together so that they try to reduce any amount of crosstalk or EMI. Then we've got two more ground lines on here and then a bunch of yellow lines. Those are all some of the analog lines. Not all of them are actually being used on this flight, but we have some of them populated and broken out so that they can go to this connector and plug in. So that's there. The wires coming out of here, and you'll actually see one of them has this kind of aluminum foil looking stuff wrapped around it. So fun fact, it actually is aluminum foil, but it's going to be wrapped up in some other stuff later. It's got some aluminum foil to help with basically reducing EMI or crosstalk between a bunch of these wires that go up here. And then also all of these wires that you see that are exposed that are going to be on the outside, they're all going to get wrapped in this eventually. They're all going to get wrapped up, and then they're also going to get wrapped in a stuff called Kapton, which is this kind of orange tape that looks like this. So it's kind of clear. It's really good stuff. It holds its stick really well even in high temperature environments. This stuff is like magic for spacecraft. So it's going to get all wrapped in there. And so you can see all the wires are still exposed right now, so then I can give you kind of this tour of all of these wires and everything. So we've got that. The black and red wires that come out of this connector, which go to all the experiment systems, those, all the black and red ones, they're all power. So they are either a like 5 volt in the ground signal. So things that are twisted together are things that kind of go together. So you can kind of see there's this little set that's twisted together. That goes to this little system right here. Another set goes over to some connector stuff over here, different things like that. If you see this kind of dangly wire right here, it's actually on purpose. So this actually is a set of wires that go through this connector, plug into Jupiter, and then what we can actually do, so these are actually connected to the battery leads of the batteries inside of Jupiter, so that then we can connect an external charger, which we have a box for that right here. We can plug it in and charge it without having to go and take everything apart, take all the batteries out and everything. So we can just use this little wire right here to plug things in. Then we tape it down before we fly. So we've got that. We've got this remove before flight switch right here. So this is another limit switch right here. We have another one over here that when these are integrated for the final time, they're actually going to be mounted inside this little this black plastic piece up here. And what those can have is they can actually have, if I grab one really quick, we have remove before flight tags that how they operate is they can actually, so we've got these little pins on them. They've got a little tag on them. And so you can take them, you can plug them in right here. And when they are in, they actually press down this little arm on the switch and close the little circuit. And then when you pull a pin out, it releases the arm and triggers, or it flips the state of the switch, so then you can use that for other things. So we have 3 different ones all on this system right here, where one of them is specific for like a RF testing activity state, which that's something that we'll be doing at something over at Wallops. We have this other one right here. This is specifically a Jupiter RBF software RBF switch right here, which basically this prevents This prevents cameras from recording stuff. This prevents an ejection signal from going on over here. It basically helps us conserve power, conserve resources, stuff like that. So when a pin is in, that means basically we're in testing mode. We aren't actively flying yet. But then as soon as those pins are out, then it's like, all right, we recognize that we are actually on the rocket. We're actually going to space. This is actually happening. So that's what those switches kind of help with. It helps make testing on the ground a lot easier. Then we have another one right here. So this is actually plugged into the ejector system, which is over in the back right here. So this right here is another software thing. It prevents cameras from triggering. It prevents an ejection signal from happening, stuff like that. So, yeah, so we've got blue for some logic signals, and then this shielded bit right here. So this is actually a shielded pair of ground and a single UART line that goes from, if I rotate this around, so we've got the ejector system over here. It has two connectors right here. We have one right here on the bottom. So this is actually direct to Jupiter. So it has a bunch of wires that go from Jupiter through this high back connector, go up through here, and then goes down into this D-sub connector right here. It's a 9-pin D-sub connector. This basically brings in power to the ejector and then also allows the ejector to then output serial data from the radio system that this is connected to when it's talking to stuff that it ejects out. So that serial line is currently shielded right now to help with signal integrity issues. And so we've got that right there. We've got the RBF right there and other things. So yeah, so this bottom one is Jupiter to ejector, and then this upper one right here. So this is actually a 15-pin connector. So this is actually ejector to peripheral systems. So this allows for us to basically have a single connector that allows power to be on or off. And then this other one is all of the peripheral systems out here. It lets this whole system talk to. So yeah, so we've got this board right here. You can kind of see this white PCB with a bunch of wires kind of dangling in front of it. So this is our ejector logic board. So this is really simple stuff. This is basically all it is if I can kind of flip this around, you can kind of see, so there's actually a Raspberry Pi Pico on there. And then we've got a handful of other things on there, which basically all it is that the it can take in power from Jupiter. It turns on the Pico, and then the Pico then can distribute power to a handful of other things. So it can trigger when some of these external cameras turn on. It can trigger when some servos actuate over on the front end. So you can kind of see there's some of these right here. These are actually the locking servos that allow things to come in and out. It also powers and talks with a radio that's actually embedded in part of the frame right here. You can kind of see, you see this little omnidirectional coil antenna in there. So there's a radio embedded in this 3D printed part, which then you can see some wires come out, go through, and then can get picked up by this board right here. So then let me grab something really quick. Thirsty boy was grabbing a drink. So we've got this main board right here, and I'll pull up the Altium schematics for that really quick. So let's see. So we designed this to actually be multi-purpose, where this can be used for multiple things. So this is a board that has functions for both the ejector and a separate system called the deployer logic board which we have in this system right here, which I'll talk about in a little bit. So, okay. So if I flip this around, so it's got, oops, let me bring this around over here. Okay. So this is the top side of the board. So this is what you can see just sticking up right here. So we have some inputs and outputs for servo signals, a battery, or not a battery, a motor right here. We have a set of inputs and outputs for like power and I2C up here, and then some other things down here for UART, an error signal, an ejection signal, RBF, and ground right there. So those then talk with a Pico that's on the other side. So you can kind of see what those traces look like. And if I flip this around, so you can kind of see how those things are. So let me flip this around really quick. Let me do some of this. Let me go to the actual schematic really quick. So swing set logic, yeah. So we have a Pico right here, which we have some pins assigned here. So Pico pins 1 through 20 right here, and then 21 through 40 right here. So we've got some of those. We have some N-channel and P-channel MOSFETs that we can use for some different things. So this is for like allowing power into the system and then allowing power to go out to a motor with a PWM signal. Over here we have some pinouts for, we've got an ejection signal where basically Jupiter, with one of the GPIO signals that it has, can output a logic high to this pin that then gets picked up on the ejection pin on here, which then the Pico recognizes that and then moves forward with the operations to actually eject the system out of the ejector. We have an error signal, which if either device has some sort of error, it can just flip that high and either one will detect it. And then we've got this UART line, which basically the data that this system picks up, it can, the system or the data that this picks up by the radio system, it is here, and then it also transmits it over this UART connection, which then gets picked up by Jupiter, goes through the RS-232 converter chip, and then gets picked up by the rocket. Then here we have stuff for 2 different servo outputs. So on here, so we've got the signal line, which is a PWM signal. We have power and then ground. And then same deal right here, just for a second servo. And then we have this motor out right here, so we can have basically the positive and negative leads of the motor hooked up to this to then drive just a simple single-phase DC motor with this. On the ejector, that isn't used, but it is used on the deployer, which I'll talk about in a little bit. So then we've got this little selection right here. So these are really just 0 ohm resistors right here, which when you populate them on the board, you can use them to basically select what voltage level you want to apply to the servos, whether you want to use just the 5-volt line, or if you want to use like the raw battery voltage that you're getting in, which is another deployer functionality I'll talk about later. Then we have the HC12 right here. So the radios that we're using are some pretty cheap little HC12 modules. They are 433 megahertz radio systems, which you can get them on Amazon for like $10. They're pretty cheap and they work pretty well. They're easy to use. They're a lot easier to work with than like XBs, and they still get pretty decent range. They do enough for what we need to do, and so it's stronger than Bluetooth, but you're not talking directly from space to the ground with these things. They work well. So there's some pins for there. So there's a set pin for like programming it. Then you've got RX and TX lines for basically data going in or out of the radio into the microcontroller. And then you've got 3.3 volt and ground. And then over here, We have a set of pins which can go to another board or get picked up from Jupiter. So this is where we get power. So on the actual board on here, really the only pins that we have populate on this connector are the 5-volt and ground lines, along with an LED line. But that's about it. And then we've got this RBF right here, which we've got hooked up to the RBF switch up here on some of the external wiring. That just pulls things high or low depending on the state of the switch. And then we have this little LED control circuit over here, which basically is just put a current limiting resistor on here, goes to a GPIO line on the Pico, and then outputs power to some lights to turn them on. There's some little, basically like headlights on the front of the ejector that turn on. So there's some of that. And then if I swap back over here, okay, so we got that. So that's this little board right here, and we've got some terminal blocks all through here, just little screw terminal stuff. And then you'll see there's a handful of other things that have been added for like periphery systems. They aren't all fully being used, but basically we've added a functionality where we can have an additional MOSFET for controlling when some external cameras get turned on, triggering them by this board. That's just a P-channel MOSFET hooked up to there. And then we have an SD card reader, which isn't being used on this board anymore, but we've got that and some other things. And then you'll see there's some stuff up here, which this is actually a very, very new addition. This is called the tumor. The acronym, I don't remember exactly what it was, but I came up with something along the lines of the Ugga Dugga Minimalist Operating Radio, which basically what happened was this system needs to be able to pick up radio signals from something that it ejects out of here. And it takes those radio signals, passes them through here, converts some stuff, and then goes through this UART line to get picked up by Jupiter to then get sent to the rocket. Somewhere along the line, there was a miscommunication between us and some software people that were working with this. And when we were doing some testing with Jupiter, we were trying to output what the recorded data was from the radios, and it was all just jumbled characters, nonsense, and everything. So we tried a whole bunch of things. We tried different software on this board. We tried different electrical things with this. That's partially why there's shielding on this right now. But couldn't figure what was going on. And so what we ended up, we couldn't figure out what happened. And so as kind of a last minute thing, so this is the end of May 2024. This project has been in the works for about 2 years now. And this little system right here did not exist more than like 5 days ago. So this is basically, we've got another Pico on here, and then we have a little micro SD card reader. If I move this, or if I pitch this up a little bit, you can kind of see a little bit easier. So there's a Pico in there, and then a micro SD port right there, and a card in there. So basically, this was designed as a just simple thing that it just takes in the raw stuff picked up by the radio, doesn't try to do any fancy formatting or encryption or whatever. It just takes in the raw stuff, records it to an SD card whenever it's powered on and hearing things. So it splits off of the radio signal. So the original ejector board, it still gets the radio signals, but the outputting, we didn't know what it was trying to transmit. And we didn't find out until after this was already made and programmed that, oh yeah, the software for it, everything is fine for this ejector board. It's just all it is is a conversion like compression thing that's running to actually make communications on this a lot smoother, which is great. But we didn't know that, and we were kind of freaking out last minute. It was like, okay, this was working just a few weeks ago, and now it's not. What happened? And so out of frustration, the tumor is now flying no matter what. It's, if anything, it's an additional level of redundancy to help make sure that we get good data back. So that's what that is. So literally, it's as simple as possible. Basically, it's just a Pico with one of its UART ports connected to a set of radio pins, so the RX and TX line, and then it has an SPI connection to a micro SD card reader up on top right here. And then one thing that's good to do, especially if you're flying anything into space or in any kind of high vibration or high intensity environments, screw down your micro SD card in some way or another. So this mechanically keeps the card from being able to slide out. So last thing you want is your thing to fly, and then you're trying to go through data afterwards and realize, oh, your micro SD card thing was shaken out and you have no data at all. So you want to keep that from happening. Just secure this and lock this down as best as you can. So that's what we've got up there. So that's the electrical for in here. We also have this little capacitor right here, which is hooked up to basically help with just some signal smoothing when activating some of these external cameras. Just helps minimize transient effects. And so then the things that come out of this connector, so all of the periphery systems that go out to the rest of this. So we've got one branch of wires that goes up and branches to two servos that go to the front of the system. I'll kind of gently kind of drag this around so you can kind of see the front now. So we have two servos right here. These are some little locking servos that basically, when we have like a CubeSat shaped unit, like a 1.5U size unit in there, these hold it in. And then when we give it a command, it'll move these arms. I'm going to be gentle with them. It gives a signal, opens up those arms, and then this spring-loaded plate back here basically goes, thunk, pushes the thing out. So we've got another one right here, just so that they're both balanced. And then also mounted on this, you'll see there's this little camera mounted right here. So this is actually an ArduCam that we basically have a USB connection that goes from it through this high-back connector and into Jupiter, plugged straight into the Pi, which the whole path looks like. So we've got this goes through this wire, goes into Jupiter, or goes into this connector right here, and comes out through some of these wires, and you can see it goes and then goes to that little ferrite bead, goes to here, literally into one of the USB ports, and then this all gets screwed down and mounted in later. So that's how that is connected. Some of the other cameras that are on this thing, those are powered by the ejector specifically. So if I rotate this back around, or actually, it'd probably be easiest to just continue over here. So we have 4 sets of ESP32 cams, which they're not the greatest, but they're pretty simple. They just they're cheap. We've got power hooked up to them, and they just start recording. So that's how we have those set up. So there are a total of 9 of those scattered around the outside of this, which if you were to play I Spy and try to find those right now, you're not going to have a great time, because a lot of them are covered up by wires and stuff right now. But we have 2 of them in the front. So we have these 2 right here, and the lenses are loose right now, but they're going to get mounted and secured down with some little like angle plates in just a little bit, and then have their SD cards cleared out and then epoxied in and everything. So there's 2 right here, which are going to be looking forward in the same direction as stuff gets ejected out of here. We have another pair kind of buried under some wires in here. You can kind of see, yeah, so there's one right there in view. There's another one right there that I'm kind of wiggling with my finger. So we have another set that's just 90 degrees the other direction. And so those are powered through, there's a set of wires that go through right here. So this little set right here, so this black, red, and green, they go through and plug into here. So there's both of those sets of cameras. The green wire is no longer being used. We were going to have like a GPIO based trigger for starting and stopping recordings, but we're no longer needing that. So we're just using black and red wires for just powering on the cameras automatically. And they have a onboard thing for just cycling through video recordings. So there's 4 cameras total right here. The 4 total ESP cams right here, along with a USB cam right here. And then kind of over in another spot, so we have this set of cameras. These are going to be looking out this way, 90 degrees from the front here. And then we have a set that right now they're on this plate, but the plate is taken off because this is actually what covers up these electronics for the ejector. And so I have it off right now, but it would basically go on something like that in a bit. And so then those look out in basically away from how things are being ejected. And so the reason we have cameras kind of looking all the way around is so the idea is these are going to be just backup cameras that, you know, if anything is going on, they're just there, they're recording. It's more data, more pictures. If anything goes wrong, we have more eyes to look at things. So that's partially why these are there. And they're all going to be angled in different kind of locations, just trying to get a full view all the way around everything. We were going to have more. So like if you look at this plate, you can see there's a hole right here. So we designed it to have more cameras, but because of power issues, we're no longer flying as many cameras as before. So there's a little gap right here, and there's some other spots where there's just unpopulated cameras, basically. But for mass, we're keeping them the same, or like keeping the same hardware for that. And then there's one more camera that I'll try to angle this around and be delicate. So if I take this and angle this up, right, so there's one all the way in the back of the ejector right here. You can kind of see where my finger's at. So this is actually going to get a view basically from like the from like all the way at the back of like the rifle barrel, looking at things as this goes and ejects out. So it'll get pretty cool view from there. And then ArduCam. So this is the actual like high quality camera right here that this is the one we really want to work. This is a much higher quality camera with trying to remember what the view angle is. It's like 120 degree field of view on here. So it's a really good camera. And so this is one that that's where we're going to get like the super good like HD shots from space. So there's that. So really all of the periphery stuff that's left for the ejector. So we've got the servos right here. We've got the blue, or not the blue, the green, black, and red cables right here for the ESP cams that go all the way out. All the rest of the wires, there's also the RBF right here. All the rest of the wires go through this kind of twisted bundle right here, which then goes to, if I move this plate really quick, that goes over to this bundle right here, which goes into the HC12 radio embedded in here, along with 4 GPIO controlled LEDs. So we've got 2 down here, and 2 up here. That basically they turn on, and they're kind of like headlights. We have them turn on as soon as everything boots up, so that it's basically just a visual indicator of, all right, absolutely everything is on and working now. Because the only way for these to turn on is if everything else software-wise boots up properly. And so there's those. Yeah. And then the last electrical thing on this whole pile of stuff right here is this little board right here. So this is this is a board right here. So this is basically a sensor package with a handful of stuff on it. So it's got acceleration, rotation, magnetometer, temperature, pressure, humidity, GPS, all that stuff, all built onto here, so that basically this is just going to be passive data logger throughout the flight, so that as soon as everything turns on, this is on, starts up the sensors, starts recording stuff, and just saves things all onto an SD card on here. And then we'll be able to look at stuff after the flight, and it's just a secondary backup source of motion and environmental data of the whole flight path, in case anything with Jupiter is wrong. And also, this is purposefully going to be mounted on the outside, so this will actually get exposed to re-entry temperatures and everything. So we should see this thing get pretty cooked. So we've got that. So this is actually based on the Trinity Avionics platform by Sader Aerospace, aka me. And then so that's there. And then this is actually similar to so there's these little picosat things, which I'll talk about in a bit, but these are actually some things that we're actually also flying, but I'll talk about those in a little bit. So we've got that. So with all of this bundle of wires, you might be wondering, all right, how the crap do you actually test this thing? So the way that we do that, we have this magic little thing. Let me move some of this really quick. So we have a magic little box that we call the rocket box. So that is this little system right here. So the way that this works is we can hook this up to a power supply, like back here. Let's see if I can bump the camera up a bit. So we have a power supply up here, and let me flip all these switches down really quick. So we can set it up at a 25. Let me bump this down just a touch. Let's see. There we go. So we can set this up as basically a 28-volt source, basically acting like the rocket, and have the leads from that go into this box. And then in here is basically a set of switches where we can flip each switch, and it'll act as GSE1, GSE2, TERA, any of the GSE or TE lines on here. Then it'll actually output that 28-volt power to the appropriate pins on this 15-pin D-sub connector, which then is where we actually plug our payload in on here. So this, on the rocket, it'll plug in straight to the rocket cable. This basically just mimics the rocket. So this behaves exactly like the rocket in terms of like the perspective of this individual connector right here. And so basically we have this black switch right here. This is our master on-off. So this turns on a light right there, and we can tell that that's active. And if we were to have this plugged in, as soon as we start flipping any of these other switches, then it's going to activate the line. So you can see, so like GSE1, if I want to activate that, I flip that switch and we have that light on. If I want GSE2 on, I can do that. I can do that with any of these, go through any configuration of stuff that I want. And so I can do that. And so I won't plug this in with all of this stuff kind of dangling out right now. It's better to do it when everything is all kind of mounted in to keep anything from getting shorted out. But in other videos that you'll probably see at some point, you'll see this thing plugged in to this connector with a power supply, and it just does things. And then all of the other stuff we've got, so we can, when we're going through operations, we can actually plug in an HDMI cable into the Pi on here and see what it's printing out like on a monitor. We can also, like if we want to see what it's outputting to the launch vehicle, we can hook up any of these lines. So we've got another mated connector which we can hook up to an oscilloscope or a meter. We can see whatever we want to make sure certain data is working fine. But for the most part, we interact more with this box a lot more. So we've got that. It also doubles up as our charging system. So on the inside, we actually have a whole charging circuit set up where we can plug in different sets of batteries. So like the the batteries in Jupiter that go through that kind of dangly lead over here. We have a cable that then plugs into one of these assigned ports, depending on which type of batteries it is that we're charging. And then we flip a switch to then start charging different things. So it's a magic little box right here. We're very happy with it. So I'm going to turn the power supply off. And then, so that is most of this stuff. So next, I'm going to talk about, let's see, I'm going to put that stuff there. Next, I'm going to talk about the deployer. So be very careful with this. So this is, let me, oh, somebody did not put that clip on right. So I put that back. And this one, move that really quick. All right. So right now this has this little like front circular plate on it and this little swivel. So this is for testing purposes. So this system is supposed to like hang and spin up and stuff. Let's see. Oops, my camera just, or my computer just went to sleep. Okay, so it's supposed to hang up, and then it's supposed to like spin around and do some things. So we have it on this swivel right now, but we'll talk more about like the electronics that are more down here. So we've got this little clip right here, which we've got a little RBF tag on it so that we can basically, if I take this off, you'll see a green LED light up. So we've got that right there. I'm going to quickly put that switch back off. So this is literally the on-off switch for this whole system. So when this is inside of the ejector in here, this limit switch is actually held down by a little plate that's at the bottom of the frame, where when it's in there, it's off, but then as soon as it's ejected and turns off, or like ejected and it's like away from the vehicle, that switch is able to then pop out. You can kind of see it sticking out right there. And then it will, let's see, let me move these really quick. Or I'll just have these hang out really quick for now. It'll just turn everything on. And then from there, what it basically does is that switch allows power to be flowing into the electronics in here straight from the batteries, and then, you know, have it start thinking and doing things. So I'm going to put this clip back on. And so move, let's see, let me move these servos up really quick. So if I flip this around, so you'll see right here at the front, so we have, oops, I moved that clip off. So you can see this board right here. So this is actually the exact same board as the ejector board over here. The only difference is that this has an HC12 actually mounted to it. Meanwhile, on here, we have it hooked up to some terminal blocks, goes through some wires, and then the radio is mounted externally over in the front. So we have a radio mounted there with an antenna right there, and then there's a Pico on the underside of this board that's kind of hidden. Then you can kind of see an all, let's see, I'll bring this camera a little bit closer. So if I can orient this right. So then you can see there's some wires right there, which those then go around to, let's see, let me rotate this around gently. If I bring this around, so some wires go to, let's see, let me get this, try to get this clip to stay on. So it goes to there. Let me move this rope. So those get picked up there. So basically, this switch when I take off the thing, so it allows the thing to turn on. I don't know if it'll focus. Let me flip that. So the limit switch basically right at my finger on the right side of it. So it's right there. So you can see there's 3 wires on the side, which, let me rotate this. Let me get this clip back on. So, and then we'll do that, move you there. Okay. And these horns on the servos, they need to be replaced. But so we've got those 3 wires, they go to here. And then when this switch activates, it allows power to go into here. And on the back side, there's a 5-volt regulator, which brings things from. So we've got 2 batteries on here. We have one right here and then one on the other side right there. So together, those are a nominal 7.4-volt source. That switch activates them and allows power to go into the regulator on the back side of this board. And then from there, we have that 5-volt power go through some of these wires right here, which then go to the logic board on the back side. And then we use a built-in 3.3-volt regulator that's on the Pico on there to then bring 3.3-volt power over back to this board and power on this B&O 055. So this is a great IMU on here, which has like absolute orientation stuff on it, sensor fusion. It's like magic. So we have that along with some I2C lines that are on here as well, which the white and the green lines right there for that. And so we got some of those. And then up here at the top, we've got, so this is where the actual batteries plug in. So you can kind of see on this battery, there's this little set of black and red wires that flows up through here. Those come up through and then plug into some of these terminal blocks right here. The other set right here does the same thing, comes to here. And so there's that. And then there's another set, which you can kind of see. There's a set of red and black wires that actually feed up through here. And actually, if I orient this right, let me move this. So they actually come up to, let me rotate this around so you can actually see. So this set of black and red wires right here. So we can actually plug in some leads right there and actually charge the batteries without having to deintegrate them here. So this is basically that. And the way that the limit switch on here is set up is, here, let's try to get the thing to focus. Let's see, remove that. There we go. So when the limit switch is pressed in like this, where everything is off, then the batteries are hooked up to only that charging port at the top. When the limit switch is off, it disengages it from being able to be connected to the charging circuit and instead goes to powering everything else on. So at any given time, these batteries are only able to be charged or be able to power stuff on. So it's a nice little kind of dual purpose use for this switch right here. So we have that. And let me show you what this board looks like in Altium really quick. So be just a second. So this we call the like the SwingSat IMU board. It's nothing too crazy, but let's see. There we go. There we go. Now we're swapped over. So this is what that board looks like. We've got a big diode on there, and then there's a placeholder for the B&O on there, and then some other info on there. So this is what those labels are for, or the labels for each of those terminal block connections are. So we've got the normally closed, normally open, and then common pins on the switch, which then their secondary uses are either V out, charge, or just straight battery connection for those. And then we've got battery 1 and 2, they're negative and positive leads on here. And then the charging leads that go up to the top of the thing. then down here we've got that set of 7 pins, which then go to the logic board on the other side of the deployer. So we've got that. We've got, let's see. So we've got the footprint for the BNO 055 on there. We've got that. And then when I flip this board, you're going to see some memes. You're going to see some goofy stuff on it. So this, we collectively as a team, we decided to put some different stuff on here just as like funnies, because when this thing is assembled, obviously you can't see any of that stuff. So you only ever see this when you're actually building the thing and putting it together. And so I can actually grab one of these boards, one of the unpopulated ones, to show you what they look like in real life. So plug back in here. So it actually came out really, really well. So these, let's see if I move it. So let's see. Actually, let me swap cameras really quick. So let me focus this. So yeah, so we've got some different just goofy stuff on there. So when you have a bunch of college students making a spacecraft, they're going to do funny, goofy, stupid stuff. So yeah, they came out really, really well. And I promise the QR code that's on there is not a virus. You can scan it. Didn't put anything on this that we wouldn't want NASA getting mad at us for if we put it on. So it's all just funny, goofy stuff. So if I go back to Altium really quick. So we've got some stuff there. And we also, on both of these boards, so both the IMU board and the logic board, we have this kind of proto board space where we can put other components if we want, which we actually ended up doing on so on the logic board for SwingSat, we ended up putting another MOSFET on there for some other trigger stuff there. So here, let's see. I bring this to there. So we can do that. So the schematic really is not that complex. Basically, you just got some LEDs that come off of the LED signal that's shared with the logic board, and then we've got some enable pins for some stuff. We've got the 5-volt regulator here. We've got the BNO 055, and then a big diode that basically keeps us from putting in batteries backwards and frying things. So that's what the so if I flip this around again, so the big chunky diode that's right here. So this big thing right here. So that's just to keep us from putting batteries in backwards and frying things. So if we were to put the batteries in backwards, it just doesn't power the system on, it blocks it. So very good to put like reverse polarity protection on any circuit that you're working on. Just good practice to do. Just do it on everything. So we've got that. And so if I return back to the logic board on here, so if we do that, and then if we go back to here, so we've got that. So we've got the motor control stuff over right here. So you can see on the logic board, if I flip this back around, so kind of up at the top right here, and I'll swap camera views again really quick. So you can kind of see at the near the top in the middle of the board. So there's this little 2-pin or like 2-terminal connection up there with a red and black wire going up. So that goes up and actually into the leads of a embedded DC motor that's actually built into here. So you can kind of see, so like The bottom of it is partially there. You can kind of see, if I rotate this around, you can kind of see there's a little bit of like the metal housing kind of visible in there. So basically the housing is mounted to the top right here, and then the shaft is attached to this set of counterweights right here, where this is part of the swing sat unit, which when this system goes up, let me rotate these so that they don't go. So when this is up, the motors, let's see, actually let me move this camera back up. Let me bring this right there. Bring that down a bit. So let me angle this a little bit. So when this system is here, it will it'll allow the motor to spin one way and the counterweights go the other way. And so that's part of that, which actually might be able to just do a quick little demonstration here in a sec. So let me take those out. And then if I hang this up and then wait just a little bit, we should see this actually start. So we move some servos really quick, and then in a minute, should see it actually start moving. You'll see what I'm talking about. And this is something that's due to conservation of angular momentum. So there we go. So it does that, and it basically it uses the IMU on board and looks at the live rotation rate that's going on, and then targets a rotation rate of 1 radian a second. And so it's going about that speed right now. I don't know if you can tell that on the camera, but so it does that for a little bit, and then it deactivates the motor. So it just needs to rotate for a little bit. I'll kind of slow this down really quick. So it does that, and at the same time, it's broadcasting radio stuff right now. So I could hook up a receiver and listen to it if I wanted, but I'm not going to do that right now. So we've got some of that. Let me plug this in, and so then this whole empty area up at the top right here. So this is actually where 4 picosats are going to be stored at. So this is where these little boys come into play. So basically, let me put this down over here really quick. So I'll rotate this. So this system right here, this area is basically set up like a spool. And on the inside, there is a servo-based release mechanism that's also tied up here. So this servo controls a set of armatures that control when some servos, or not some servos, some tether-based picosats basically extend out, and then also when they actually release and separate from this. So this is just a momentum exchange tether technology demonstration for like small-scale CubeSats. So, yeah. So this system, we can basically have, so the tethers, we've got little grommets on the ends, which they can go in, and then we go through a whole locking procedure that basically moves an arm in place that puts basically a little pin through this grommet and locks it in place and keeps it from being able to pull out. And so we can do that. We'll have a set of 4 of them, basically all wrapped around. And then once they're in, basically we can go through, wrap it around just like a tape measure. I'm not going to wind that whole thing around right now, but in the end, we'll basically end up, so if I flip this around, we'll actually have, let's see. So we'll basically have the picosats all wrapped up in, and I've got this little, let me move this little RBF clip off really quick. So I got that. That turns that on. All right. So when actually, let me see if I can do it this way. So when they are in here, there's a little locking system that keeps them in place. Let me play with that. That needs to get played with just a touch, but basically this holds them in place, and then when the release mechanism occurs, it's going to have these flop out and then turn on. These actually have a little limit switch on them right there, which when I push that, that turns power on and off there. So they come out, they start unfurling, they start recording data, and then they'll be out here basically with this as this all is swinging around. So now, look at that. I might put this little clip back on really quick. Let's see. Got these little clips on that go over the limit switches to keep them from turning on. So we've got that. So now I'm going to move this out of the way. Put that back there. So now I'm going to talk about these bad boys right here. So these are also built on the Trinity Avionics platform, which is also this little board right here. So we have one of these here, and then we have 4 of these, which are each going to be on these little tape measure tethers. So these basically are set up where, so you've got the board itself. We have this little set of leads right here for battery charging. The other side there goes to, if I kind of flip this around, you can kind of see these tape measures are huge. They're about 1 meter long each. So the leads go to, they go from right here, they go to this little 3.7 volt battery right here. Those are mounted, taped down to this little 3D printed fixture, which then also attaches to the tether right here. You can see this right here. So this is a little shield right here that I designed for these boards where, let's see if I can get this to actually stay on right. Let's see, let me do a quick little thing. All right, so this is a little shield where kind of on the inside, you can kind of see kind of sandwiched in there, there's actually an HC12 radio that's embedded in there, which then has its has an antenna right there sticking out. So this is how that little antenna then talks through the radio mesh network to the deployer and to the ejector and gets picked up. And so this is basically broadcasting its recorded motion data from some IMUs that are, or from an IMU that's on here. So we've got a little B&O 055 on there. And so this board, I'm not going to show through the PCB design in length, but it's got a whole ton of things. And there's also a bunch of improvements that are also going to be implemented on the next generation. But here are some things. Here's some things right here. We've got a USB-C connector. We have a USB to serial converter chip on here for programming. We've got some stuff right here for uploading code. We've got some stuff for power management right here. We've got a buzzer. We've got reset and boot buttons. We've got some LEDs. We've got some headers down here. We have an ESP32 based SoC over here. We have a micro SD card slot. We have a GPS. Then we have an IMU, environmental sensor, and a high G accelerometer on there. So those are there. And then on here, I go to 2D. So this is actually a 4-layer board, and it is like dense. I'm not going to go through it all, but here it is in all its glory. It's lots of things on here, and also definitely some things that can be improved, but that's going to be on a future thing. So we've got that. And so, yeah, that's a whole load of just stuff. So the whole radio network, the deployer, which I was spinning around a bit ago, and the ejector, they all talk to each other, and all of the motion data of these things from this momentum exchange tether demonstration, all of the motion characteristics of each component of that system, it's all going to get recorded by the ejector and then pulled by Jupiter, then transmitted to the rocket and saved locally. And so, yeah, I think that is it for all of the. I think that is it for all of the electrical systems on this spacecraft. So, um, yeah, we got thingies. We got a whole bunch of wires. So, um, let's see. Yeah, let me flip this around. So, let me bring this up. So, yeah, so that's basically it. So, basically, next plans at this point are so we've got all these electronics. Next, what we're going to do is we are going to put some RTV on some of the electronics, and then also put them, like, screw them into their enclosures for the last time, so that they don't just hang and shake around and whatnot. You never want to have any components relying purely on, like, any heavy stuff, so like any through hole mounted stuff or anything that you've got wires dangling off of. You never want your whole strength for mounting those to just be the solder joints. It's good to have some sort of either RTV, some sort of epoxy, some sort of screw, like fastener mechanism, um, something like that to hold them in. So we're going to do all of that. We're going to Loctite all of those fasteners in for the final time, lock everything up, and then so we've got that. We'll put the lids on all of the enclosures for the last time. That'll mainly be so we've got these gaskets or O-rings or seals on each of these different enclosures. Basically, we put some high vacuum grease on each of them, put them on, and then screw the lids on with Loctite so that the screws or the fasteners are in there permanently. And then we also are going to put like a little line of RTV around the seams, just help keep with extra sealing. And then on top of that, we'll put a little line of Kapton tape wrapped around it. And so that'll be wrapping up those enclosures. And then on each of the wires, we're going to wrap them up in foil, and then going to cover them in Kapton and tape them down, stake them down so that they don't move. And then things will all be screwed down, taped down, everything for the last time, and then it'll be ready for flight. So, yeah, we're very close at this point. We're within just a few days of having everything be like done, flight ready, ready to get shot into space. It's going to be great. So, yeah, if you have stuck around this video this whole time, I salute you. It takes a lot of guts or patience, really, to listen to me ramble on this stuff for a long time. But hopefully, you learned something along the way. Hopefully, something useful, whether it's you're working on this project and using this for like future reference, or if you're completely new to spacecraft development in general. Yeah, just this is some stuff, like, obviously this isn't an orbital spacecraft. This is suborbital. This is stuff that goes up and then comes back down. This is not something that is flying for years and years in space, because some of this stuff I would not trust on one of those kinds of flights, because you've got radiation and temperature extremes, which At that point, you start needing better like radiation shielding and also like thermal systems to make sure things don't get too cold or too hot. With this, we've got stuff where we have enough insulation for things to keep them from getting too hot during reentry, but that's really all we need in terms of thermals. And so, orbital stuff is a little bit more involved, but this is at least something that, yeah, this will work for suborbital spaceflight, and then also um, a bunch of these principles can be used to help inform the design of whatever other systems you might be working on, like on the ground. So, um, yeah. So, I think that's about it. Thanks for listening to me ramble, and hope you got something from it. And I'll see y'all later.